Welcome. This is 1 a day 12. This is example 1. In this question, it asks, suppose that now that our object, should word that better, from the point x0, y0, rather than from the origin. Resolve the original differential equation with the new initial conditions. So t of 0, we're not launching from the origin anymore. We have some new location, x naught, y naught. We want to resolve the differential equation. Okay, so we know that acceleration is equal to d squared r over dt squared. Velocity is dr dt, which is negative gt in the j hat direction plus some constant vector, and then v naught is equal to the 0 vector plus that constant vector. Okay, and so what do we need to do? Well, we're trying to resolve all the components. So we're going to go through everything. Okay. All right. So to start off with, we know that the r of t, the original one that was given to us, is of the form negative 1/2 gt squared in the j hat direction plus v naught t plus some constant vector we'll call k, just to distinguish it, where k is implied up here, where k is given by the form x0 in the I hat direction plus y0 in the j hat direction. Okay. All right. So the question then is, what do we need to do to resolve the equation to accommodate the new point? Okay. All right. So let's go ahead and plug in what we're given, and let's see what we get. We get negative 1/2 gt squared in the j hat direction plus v0 is going to be broken down. I guess maybe a picture would be helpful here. So let's look at that. Let's consider it and kind of see. Let's motivate where these pieces are coming from. So originally we had something look like this, and then our path of our trajectory would look something like that. But here we were assuming we were coming from the origin. So imagine that we're not here anymore, but rather we're, let's say, at some point here. Well, this is our x naught and our y naught. This is the initial condition. So this curve is that's no longer what we're following. So if we want to know how to adjust from our original, if we're starting over here, then imagine a vector emanating from the origin to that point. Okay? Then the angle alpha that corresponds to this value, we can shift our original along this x naught direction by considering the cosine of this alpha. And then likewise, so this bit here would be just y naught sine of alpha. That's the component along that direction. Okay. And so let's go ahead and show that relationship with respect to, that's a v naught, looks like a y naught. And I think I said y naught because I was looking at y naught. This is a v naught along that direction for the velocity, and this is then the v naught cosine of alpha along the x direction. So that's how the velocity from our new position, right? That's how our new position is here. The velocity is going to change as we move our axis in that direction. So v naught then is going to be, we're using the vector notation, it's going to be v naught cosine alpha, and then v naught sine alpha in the j hat direction. So this is writing it component wise, and this is going to be times t plus, and then we have an x naught and a y naught in the as the constant term. And I'm going to go ahead and switch this to 0, and I'll erase the j. There. That way it's all in the similar form. So you can kind of see how all of the pieces fit together. Okay. All right. So all the X's and then are all the I hats and all the J hats component wise can fit together. So we can simplify that a little bit more. Think out. So we get what do we have? We have X naught plus V naught T cosine alpha in the J hat direction. And then we have Y naught plus V naught sine alpha T minus 1/2 GT squared in the J hat direction. So there is our corresponding resultant vector for the situation where the new initial condition is inserted. Right. For the total time of flight, then, okay, for the total time of flight, okay, so for the total time of flight, we just need to take the y component here. So set y equal to y naught plus v naught sine alpha minus 1/2 gt squared. This will give us the time that it's in the air and set it for when y is equal to 0. Okay, so use any method, but the quadratic formula, for example, would work. This is just a scalar quantity at this point, and take the largest, choose largest. Okay, that'll be the result. I trust that you're capable enough to figure out how to solve those V naught, Y naught, G, and alpha would all be given information, so you just plug it in and solve. Okay, so that is actually like an algebra 2 problem back in high school kind of thing. Okay, so that should hopefully be pretty straightforward. All right, and then find the maximum height. All right, so now we want to find the max height. Well, this is a parabola, and so it's just the vertex, right? The max height. So you could use t is equal to opposite of p over 2a. This is the time of max height. And then plug it in to find it. Or you can take the derivative dy dt and set that equal to 0 to find the exact value. And if you did that, you would get t is equal to v naught sine alpha over g. Okay. Which is probably no surprise that that is the t component of the vertex. Okay, and then if you wanted to find the max height, just take this value and plug it back into y of t. So take this t into there and plug it in. Okay. And find the range. Okay, and then the last one is the range. Okay, so range is the whole thing of flight. So this is the range. And that's what we're looking for. And so to do that, you can use x is equal to x naught plus v naught t cosine of the angle of elevation when y is equal to 0. Okay, so that gives us then that x is equal to x naught plus v naught, and then some really fun stuff. I'll go ahead and enter that. This is v sine of alpha plus the square root of v naught squared sine squared alpha plus 2 g y naught. Okay. With all going underneath the radical, all divided by g. And then right here, there should be a cosine alpha as well. So if that's not clear as mud, I don't know what it is. Okay. So this is the result you get from our original problem up there. And that plugging in that value, this is for when y equals 0, which is the result you get from the time of flight problem. So when you solve this for the quadratic formula, this is the result of that. Okay, so you just plug it in. And I hope that was helpful. And I'll see you in the next video. In this example, this is example 2. In this example, it says a golf ball is hit with an initial speed of 116 feet per second at an angle of 45 degrees above the elevation from a tee on a green that is elevated to a tee that is elevated 45 feet above where the tee is shown. Assume that the pin is 369 feet downrange. Will the ball land in relation to the pin? So we want to know, where does the ball land in relationship to the pin there? Okay. All right. So first of all, let's assume that where we're at right here is the origin. So that's going to be 0, 0. And what do we know? We know V naught is equal to 116 feet per second. We know alpha is equal to 45 degrees or pi over 4 radians. We know that x is equal to x naught plus, not plus, sorry, x naught t cosine of alpha, and y is equal to what? V naught. Let's go y. I have these and there we go. V naught t sine alpha minus 1/2 gt squared. Okay. So the nice thing is we know that x naught and y naught are 0 here. So you don't see them showing up in the problem there. And let's see. Okay, let's go ahead and use this information to solve. So note that the height of the pin is at 45. So y is equal to 45 feet. Okay, so when does that occur? Let's set this y equal here. So v naught, we have, I'm going to do this in general just because I don't like plugging in numbers right away. If that's confusing to you, replace it with numbers. So I'm going to call this this y, y, this is what I want, is y final is 45 feet. So that's what I'm looking for. Okay, so when y is final is equal to v naught t sine alpha, that's alpha, is t, minus 1/2 gt squared. Okay, so I need to figure out if and when that is possible. So I'm going to subtract over the y f and set this equal to 0 and solve for t. So is there a time when this this ball gets up to that height, to see if that's even a possibility? So I'm going to subtract over the y final and then use the Pythagorean, or the Pythagorean, use the quadratic formula for t. So I get, so I'm going to subtract over this y final. So that's what I'm solving. Okay, and so t is going to equal opposite of b, so v naught, sorry, sine of alpha. That's this thing. That's b, opposite or plus or minus the square root. And this is that big ugly thing you saw in example 1 being plugged in. V naught sine of alpha squared minus 4 times negative 1/2 g. That's a c y final divided by 2a, which is negative 1/2 g. All right, and so This is a point where numbers are probably easier, so I'll plug in the numbers. So V naught is 116. Sine of alpha, or sine of 45 degrees, is square root of 2 over 2, plus or minus. The negative that's down here will affect the negative here, and we'll just switch those as plus minus. So you can choose to do with that as you wish. Square roots of, well, we have sine of 45 is 1 over square root of 2. So it's also the same thing with a square. It's going to be a half. So this is going to be 116 squared over 2 minus, well, plus 2 times y final, which is 45, all divided by negative g. And g for us will be 32. Okay. And so if we plug in all that fantastic information, this turns out to be getting 82.02 plus or minus 62.2 over 32. Okay. So this gives me then that either it's 0.0625 or it's 4.501. Okay. So we'll choose this one because that'll be the time of flight. Okay. And so now that we know how long it's in flight, we can use the other equation here to determine where it ends up going. Okay. That's x naught. That's v naught. It was like x naught 0 there, so that's why. Okay, so so x is going to be v naught, which is 116 feet per second times. Oh, should I throw that up here? Okay, so that's v naught. Let me write it out. So x is equal to v naught cosine alpha t. And now we know what each of these components are. So v naught is 116 feet per second. Cosine was square root of 2 over 2 because the degree is 45. And then time is 4501. So that's going to give me how many feet it is. Plugging in each of those numbers, we get 369.19 feet. So that's how far it went from went back to our original one. So it went, well, actually, that's really close. Went 369.19 feet. Our original one had 369 feet. So the difference is 369.19 minus 369 feet is 2. Is it 19 feet? That's not obvious, which is approximately 2.3 inches. So it's super close. That's a heck of a shot. All right, I hope that was helpful, and I'll see you in the next video. This is example 3. It says to open the 92 Summer Olympics in Barcelona, bronze medalist archer Antonio Rebelo lit the Olympic torch with a flaming arrow. Suppose that Rebelo shot the arrow at a height of 6 feet, so that's him shooting the arrow at 6 feet, above the ground level from 90 feet from the 70-foot hot cauldron, and he wanted the arrow to reach a maximum height of 4 feet above that. So 74 feet is where he wants the arrow to hit above the ground. So we want to express Tmax in terms of the initial conditions, V naught, and a firing angle alpha. Use y max equals 74 feet in the result of A to find the value of V naught sine alpha, find the value of V naught cosine alpha, and then find the initial firing angle of the arrow. Okay. All right, so we have a couple things to do here. All right, so we know x is equal to x naught plus V naught t cosine alpha, and then y is equal to y naught plus V naught t sine alpha minus 1/2 gt squared. Okay. Here we know from our initial point here that our origin will be at 0, but 6. So x naught and y naught. And what else? V naught, we don't know. V naught, we do not know. Okay, let's go ahead and dive into it. So the first part of the question was to find out T max. Okay, so when is the y at its greatest height? Well, if you remember from the last one, it's in dy dt is equal to 0. But for us, we also know that since this is a parabola, is the y coordinate, or the x coordinate, if you will, or the t coordinate, really, of the vertex. So you can take the derivative. That's just no different than looking at negative b over 2a. So t max occurs at opposite of b over 2a, which is minus v naught sine alpha over negative 1/2 g. So the negatives cancel. And we get this is v naught sine alpha over there's a 2 naught v naught half flipping up to the top. Um, let's see. So what is this? This is v naught sine alpha. That's a derivative there. Minus taking down the derivative is g of t equals 0. Okay, so v naught sine alpha over g is equal to t max. Okay. Right, so this is the value there, taking the derivative. I was having trouble rectifying why there's a half and a 2 there and there's not in this. So anyways, that is interesting. Okay, so that's the T max, the time for the maximum height. And so we wanted to know what the maximum height was. We could plug that in to the one here. Okay, so if we did that, we'd have the y max is, well, let's just go ahead and put in the numbers. I think that's doable for this one. So 74 is the y max that we want. The initial height was 6 plus t max. T max v naught sine alpha, since we don't know what those values are, minus, since this is in feet, right, half of 32 is 16, t max squared. All right. What can we do? Subtract over. And we know that T max is the V naught sine alpha over G. So, which is 32. Okay, so let's see if we plug in the information and simplify. We're going to get 68 subtracting equals what we have V naught. Oh, actually, you know what? There's a common sine alpha over 32 minus, interesting. We have V naught sine alpha squared over 64. those subtract, leaving a half. Yeah. So that's going to be V naught sine alpha squared over 64. Multiplying both sides by 64 and taking a square root, we get 68 times 64 is 4352 equal to V naught sine alpha squared. Taking the square root, then you get the square root of 4532 is equal to V naught sine alpha. Now, it doesn't tell you anything about, this tells you that the product has to equal that amount. Okay. So that's perfect. That's all we need. So T max is equal to V naught sine alpha over 32, which means that the square root of 4532 over 32. And so that gives it T max. And this is a numerical value now, so we can plug that back into V naught cosine alpha, which is equal to 90 over times 32, that's gravity, divided by the square root 4532, which gives us 2880, square root of 4532. And so now we have two nonlinear equations and two unknowns. So let's go ahead and here's one, here's two. So let's go ahead and use those two. We can take a ratio, V naught sine alpha over V naught cosine alpha. Nice things there. Those will reduce to a single function. This is going to give me tangent of alpha. And what is that equal to? That's equal to 4352 divided by 2880. Which implies then that alpha is approximately 56.5 degrees. Okay, which then says, plugging that back in for V naught, that we have square root of 4352 divided by sine of 56.5 is approximately 79.1 feet per second. Okay, which I think was everything that we were looking for. All right, I hope that was helpful, and I'll see you in the next